So we've come to our zombie apocalypse section of the slide, how to calculate an ANOVA by hand. So no matter how we're actually calculating the ANOVA, whether we're doing it by hand, a scientific calculator, or we have access to a statistical package that'll do it for us, there is still the same process that we're going to do that we do for all statistics. The first one, of course, is to determine our hypotheses. We should always have hypotheses and hopefully directional hypotheses based on past theory and past research or through logical induction or deduction before we ever conduct a statistical test. We want to set the criteria for significance. Generally speaking, we want to determine the alpha, usually set, of course, at 0.05. We want to make sure that we calculate the degrees of freedom, because the degrees of freedom basically are telling us how powerful that test is. And again, we're going to use those degrees of freedom to figure out what is the minimum test statistic, the calculated F that we need to be able to claim that there is some difference somewhere in our data set that is most likely due to meaningful effect and not chance. In other words, we're 95% confident with an alpha of 0.05. We're going to find that critical region based on the degrees of freedom in the F distribution table, and based on that, we're now going to do the hand calculations. We're going to compute the sums of squares within and between. So the sums of squares within is going to be looking at the total variance, including error. The sums of squares between is going to be looking at the actual differences between the groups. We're then going to compute the mean of squares to create the F ratio. We're then going to compare that F ratio to the critical F value, and we're going to state our conclusion. Either there is evidence that there is a meaningful difference across groups and it is statistically significant, or it's not. So to calculate an F ratio, F is calculated by looking at the mean squares of both between and within. And mean squares is simply a measure of variance. Variance is the sum of squares divided by the degrees of freedom. So if the null hypothesis is true, the treatment effects are equal to 0. There is no significant difference. The between group variability will equal the within group variability, and the expected value of the F is 1. So if there's absolutely no effect, and you calculate an F of 1, that's what it's telling you. There is no difference. There is no effect at the top that's different than what's at the bottom. The F ratio is 1. You got the same value. What we're hoping for is a larger value at the top of the equation than the bottom, which gives us an F of above 1. Now, because everything's being squared and everything is positive, we should never calculate an F and get less than 1.0. 1.0 is no relationship whatsoever. Now, the top of the equation is, again, the mean squares between, and what the mean squares between is basically a summation of the sums of squares between divided by the degrees of freedom between. And the bottom of the equation is the mean of squares within, which is sums of squares within divided by the degrees of freedom within. So we're going to take this apart and first look at the top of the equation. How do we get the top of this equation to calculate the F? How do we get the mean squares between? So what we're going to start with on the top of the equation, and again, this is a between subjects, one-way, single variable ANOVA with 3 conditions. And our 3 conditions is a criminal group, a non-criminal group, and an unknown group. And in each group, we have 5 participants. And remember, they're different. There's 5 criminals, 5 non-criminals, and 5 people that we don't know the background of. And we get their outcome, the DV, their individual scores. So the criminal group, person 1 had a 10, person 2 had a 7, person 3 had a 5, person 4 had a 10, person 5 had an 8. We're going to add these together. We're going to get a sum of their scores, 40. We're going to divide by the number of people in that group, 5, to get a mean for the criminal group. 40 divided by 5 is 8. The non-criminal groups, the sum of all their scores is 20. 20 divided by 5 is 4. And the unknown group is 25. 25 divided by 5 is 5. So we now have the means of the 3 groups. We have an 8 for criminal, a 4 for non-criminal, and a 5 for the unknown. And since the top of the equation is looking for the differences in groups, we're halfway done. So the top of the equation is pretty quick and easy to calculate. So what we're now going to do is calculate the grand mean across all 3 conditions. And the way we do that is we add up the means from each group. So the first group is in that first row, a 4. The second mean is in that next row, an 8. And the final mean was a 5. We're going to add those together. 8 plus 4 plus 5, and this is the first column, sample means, is a 17. Now we need to get the grand mean. The grand mean, well, there's 3 groups. So 3 means divided by 3. 17 divided by 3, which is the very bottom left of the page, is 5.67. That is our grand mean. What we're now going to do is take the mean of each group minus the grand mean. So 4 minus 5.67 is negative 1.67. 8 minus 5.67 is positive 2.33. And 5 minus 5.67 is negative 0.67. Now, again, I told you all numbers in these equations are going to be positive. We're doing the sums of squares. So we're now going to square those. So negative 1.67 multiplied by itself is 2.79. This is that last column, square deviation from the grand mean. 2.33 multiplied by itself is 5.43. And negative 0.67 multiplied by itself is 0.45. We're going to add all of these together. We now have the sums of squares. But remember, the top of the equation was sums of squares divided by degrees of freedom. This is the degrees of freedom between groups. And again, it's towards the upper left. And what the equation for this is k, the number of groups, minus 1. In this case, we have 3 groups, minus 1 is a 2. So we're going to divide by 2. 8.67 divided by 2 is 4.34. So that's the sums of squares. Now we're not quite done with the top of the equation. We're going to still do one more step, but let's just focus on that bottom right. So we have our square deviation from the grand mean, that 8.67. We've got our degrees of freedom, 3 groups, the smallest number you can have with an ANOVA, because if you only had 2 groups, just run a t-test. You've got 3 groups, 3 minus 1 is 2, degrees of freedom of 2. So 8.67 divided by 2 is 4.34. But what if there had been 4 groups? Then our degrees of freedom between would be 4 minus 1, 3, so that 8.67 would be divided by 3. Notice that would give you a smaller number. The more groups, the smaller the number is going to be on the top of the equation. And this is why, again, it's kind of a visual representation, a mathematical representation of why larger, more complex ANOVAs with more and more groups become harder and harder to find meaningful differences and claim they are significant. And it's happening right here in front of us. That degrees of freedom is a part of the equation, and it's reducing the strength on the top of the equation of that mean difference. The more groups you have, the bigger the difference between those means have to be before we can confidently say it's due not to chance. It's actually due to systematical differences. Okay, so let's hold on to that 4.34, the sums of squares between. And now what we need to do is to actually get it to mean squares, we take the sum of squares between and we multiply it by small n, the number of people that were in each group. So in this case, though we had 3 groups with 5 people each, so our big N, total number of participants is 15. The small n, the number of people that are actually in one group, is 5. Now this hand calculation of ANOVA really works best if you have an equal number of people, even though they're different in each group. There are some adjustments, but we're not going to really touch on those there within this because we're wanting to keep this fairly simple. Again, my goal in these equations is not necessarily to punish those people that hate math. It's not necessarily believing that at some point you may have to hand calculate an ANOVA. I'm assuming that if we actually hit the zombie apocalypse, the last thing we're going to be doing is social science research. But it's more about trying to help you understand how these equations are working and why it's so important methodologically to make sure you've got good group differences, that you're not just throwing extra groups in for no good reason, and that you're being very systematic and thoughtful in how you design studies based on knowing how the math is going to work and how it's going to increase or decrease your chance of finding statistical significance. So anyway, for our top of our equation, we have our sums of squares between divided by degrees of freedom between. That's that 4.34. But now we need to create it over to mean squared between, and we're just going to multiply it by, again, small n. So 4.34 multiplied by 5 people in each condition, is 21.7. We now have the top of our equation. That is our mean squared between, 21.7. The bottom of the equation is going to look a little more familiar. It's going to be more similar to what we were doing with multiple regression because, again, what we're doing is just calculating total variance. So once again, we do need those means: criminal group of 8, non-criminal group of 4, unknown group of 5. Based on those, we're now going to do the deviation of the mean of each group. So for the criminal group, our mean was 8. So 10 minus 8 is 2, 7 minus 8 is -1, 5 minus 8 is -3, 10 minus 8 is 2, and 8 minus 8 is 0. And again, we're going to sum those up. Well, actually, not yet. We're first then going to square them, because again, everything's positive. So we're going to square the deviation from the mean. 2 times 2 is 4, -1 times -1 is 1, -3 times -3 is 9, 2 times 2 is 4, 0 times 0 is 0. We're going to sum those up 18. Our sum of squares for the first group is an 18. We're now simply going to repeat that process for non-criminal, sum of squares 20, and repeat that for the last group, sum of squares 26. So at this point, we're simply going to now add up our sums of squares. So we're going to take our squares and we're going to sum them. So again, we're adding 18 plus 20 plus 26, which equals 64, and we're going to divide it by the degrees of freedom within. In this case, the degrees of freedom within is n minus k. So the total number of participants minus your number of conditions. So again, the larger this number is, the smaller the bottom of the equation is going to be. So again, in this case, we have 15 participants total, 5 in each group, big N, minus the number of conditions, 3. So 15 minus 3 is 12. The top of our sums of squares between calculating means of squares within is 64 divided by 12. Now let's again think about the power of having more participants. If, for instance, we actually had 67 participants, 67 minus 3 would be 64. 64 divided by 64 would be 1, a much smaller number. So again, as we increase the number of participants, we get a smaller number on the bottom of the equation. In other words, the more people we have, the more we can trust that if there is differences in the top of the equation, they are probably happening due to actual meaningful effect, not just random variance. But also notice that k comes back again. If I actually, again, in this case, we had 15 participants with a k of 3 groups, so it was a 12. But if we actually had 15 participants and we had a k of 5, then 15 minus 5 is 10. 64 divided by 10 is 6.4. The number on the equation just got bigger. So again, not only can we reduce the size of the number at the bottom of the equation by having a larger n, it also gets bigger on the bottom of the equation the larger the number, or the bigger the number, or the more conditions we have, because it's n minus k is what's going to the bottom of that equation. So again, I really want you to just kind of conceptualize what's happening mathematically in our determining if we actually have statistical significance, because it does matter about ways that we methodologically reduce error to make it less likely that the number at the bottom is bigger. We also can help our study or make it more powerful by having a streamlined study with only the groups or conditions that we need and having larger numbers of participants. So now that we have these two numbers, we just put them together. So the top of our equation was 21.7, the bottom was 5.33. So 21.7 divided by 5.33 becomes 4.07. That is our F score. Our F is 4.07. So we have calculated the ANOVA, the omnibus test, that's going to tell us, is there significant meaningful differences between our groups? Now, how we're going to report this is, again, we're going to have F capitalized in italics. We're going to then have a parentheses with our degrees of freedom between, followed by a comma, followed by our degrees of freedom within. So again, our first number is k minus 1. So a 2. That also means anytime you read an ANOVA, if you see an F of 5, you know they had 6 conditions. If you see an F with a degrees of freedom between of 4, you know they had 5 conditions. If you see a 2, you know they had 3 conditions. The next is n minus k, so 12. Now again, once we know from that first number what the actual number of conditions were, this can also tell us the end of the study. So again, if we know that the first number is a 2, that means that the number of groups was 3. And if the second number is a 12, well, 12 plus 3 is 15. That tells us their total sample is 15. So though degrees of freedom here are basically a notation letting us know what was the bar we had to pass for us to claim statistical significance, there is also information in there that tells us at a quick glance, with the knowledge of how those two numbers were calculated, not only how many conditions there were, but also how many total participants were. We're going to follow this up with the actual value of f, and then finally whether it's significant. And again, that's the final component. Is it significant? Was that 4.07 a large enough value for us to claim that there was a 95 or greater % chance that it was systematic differences and not due to chance? And we do that with one of these tables. So again, we're going to look at the top of the equation. Across the columns is the degrees of freedom numerator. That basically means your degrees of freedom within. And then the degrees of freedom denominator, your degrees of freedom within. So again, between at the top, within along the side. So in this case, we're going to go to 212 and see that for a 5% value, we need a 3.88 or larger. And right below it is what we need for a p of 0.01. So our value actually fell between these. So we did not make it all the way to 0.01, but we definitely did pass the bar of 0.05. So our p is less than 0.05. We have statistical significance. If we were running this test in SPSS, we would get a table that looks like this. And I just kind of want to walk through where these same numbers are going to be found in this table. So whatever the name of your outcome is, your DV is going to be the first thing you're going to look for, and it's usually going to be the third line. You're going to see your sums of squares, you're going to see your degrees of freedom, and you're going to see your mean square value. You're going to also then see your error, which is the bottom of the equation. And again, you're going to see your sums of squares, error, your sums of squares, your degrees of freedom, and again, the final mean square value. At this point, that also then gives you your F, your significance, and in this case, your effect size. Effect size for ANOVA is usually partial eta squared, and we'll talk a little bit more about effect size moving forward. So again, our F, our significance, and our effect size. So if I was going to report this particular F, I would report F, parentheses, 2, 27, parentheses, equals 14.93, p of 0.00 or less than 0.001, comma, partial eta squared 0.53, rounding it to 2 decimal points.